The electric force is a force that arises from the interaction between two objects that have electric charge. We can consider it to arise from the electric charge of one object interacting with the electric field of the other object. This interpretation is consistent with the units of electric field, which you recall are newtons per coulomb. This is the equation for the electric force acting on a point particle. It depends on the electric charge of the point particle and the electric field experienced by the point particle. This is not the electric field of the point particle itself, but rather the electric field from the other objects in the system that interact with the point particle. If the electric charge of the point particle is positive, the force is in the same direction as the electric field. If the electric charge of the point particle is negative, the force is in the opposite direction of the electric field. Since electric fields point from high electric potential to low electric potential, the electric force pulls positively charged particles toward lower electric potential and negatively charged particles toward higher electric potential. It follows that high electric potential corresponds to low electric potential energy for negatively charged particles. Similarly, low electric potential corresponds to low electric potential energy for positively charged particles. This is consistent with the equation for the electric potential energy of a charged point particle in an electric potential. The electric force between two charged point particles, A and B, can be considered to arise from the interaction of the electric charge of particle A with the electric field of particle B. Alternatively, we could consider this electric force to arise from the interaction of the electric charge of particle B with the electric field of particle A. Either interpretation gives the same final expression, as expected from Newton's third law. In these calculations, we have determined only the magnitude of the electric force between A and B. The direction of the force will result in A and B being pulled together if their charges have opposite signs, and being pushed apart if their charges have the same sign. Now let's calculate the electric force that exists between a uniformly charged rigid rod and a uniformly charged disk. The rod is aligned along the longitudinal axis of the disk. We can consider this electric force to arise from interactions of tiny bits of electric charge in one object with the electric field of the other object. If these bits of electric charge are infinitesimally small, we can model them as point particles and use the equation for the electric force acting on a point particle. Although we can model either object as a collection of point particles, it is easiest if we model the rod. The reason for this is that we already have an equation for the electric field of a disk along its longitudinal axis, and thus we have an equation for the electric field of the disk at any point along the rod. We do not have a similar equation for the electric field of the rod at every point in the disk. Thus, the variable dq in the equation will be an infinitesimal bit of electric charge in the rod, and the variable E will be electric field of the disk at any point along the rod. We are thus solving for the electric force exerted by the disk on the rod. As we've done before, we can replace the variable dq with the product of the linear electric charge density, denoted by lambda, and the variable dz, which denotes an infinitesimal bit of length along the rod. Since the rod is uniformly charged, lambda is equal to the electric charge of the rod divided by the length of the rod. The total electric force experienced by the rod is the integration of the contribution from each infinitesimally small bit of electric force acting on each infinitesimally small bit of electric charge in the rod. The limits of the integration are from d to d plus L. In other words, the closest any bit of electric charge in the rod can be to the center of the disk is d, and the farthest any bit of electric charge in the rod can be to the center of the disk is d plus L. Many of the variables in this integration, including the unit vector, are constant and can be taken outside the integral. The remaining integration is straightforward. If the electric charge of the disk and the electric charge of the rod have the same sign, the force is along the positive z-axis. In other words, the rod will be pushed away from the disk. If the electric charge of the disk and the electric charge of the rod have opposite signs, the force is along the negative z-axis. In other words, the rod will be pulled toward the disk. This figure combines everything that we have learned about the electric interaction. Electric potential and electric potential energy are related to each other by our equation for the electric potential energy of a point particle. We can use integral calculus to apply this equation to systems that aren't point particles. Electric field and electric force are related to each other by our equation for the electric force acting on a point particle. We can use integral calculus to apply this equation to systems that aren't point particles. Electric potential energy and electric force are related through differentiation and integration. This works because electric force is a conservative force. Please notice that when integrating the electric force, we determine only a change in electric potential energy, not the absolute value for the electric potential energy. Electric potential and electric field are related through differentiation and integration. Please notice that when integrating the electric field, we determine only a change in electric potential, not the absolute value for the electric potential.